Today's speaker is Juan P. Garrahan from the University of Nottingham. And he will tell us today about kinetic constraints and slow dynamics and non-ergodicity due to kinetic constraints and going from classical to quantum regimes of dynamics. So let's start with Professor Juan P. Garrahan.
Okay, thank you very much. I'm happy to be here at a distance. And I will share my screen. So I will share the screen. So can you see that?
Yes. Yeah, please.
Can you hear? You can hear me all right?
Yeah. Yeah.
Okay. Yeah. So what I want to do is give an overview of a crossover of ideas between classical and quantum many-body physics, in particular around the problem of slow dynamics and non-ergodicity. And I will try to emphasize the main concepts and not necessarily discuss too much discuss too much the details. But of course, I'm very happy to go into the details if you have any questions. My aim is to try to convey the main ideas in the next, 40-45 minutes. So this is my plan. I'll split the talk in two parts. The first part will be classical. So I will cover the basics of slow dynamics in classical many-body systems. What are the essentials? What we know? What are the open questions? And think of how to address those questions in statistical mechanics through models that are called kinetically constrained models. So that's the first part. And then the second part will be trying to translate these ideas to quantum many-body systems. So I'll discuss, brief review of what we know as a community in physics about relaxation of quantum systems and non-ergodicity, and then translate, this way of modeling slow dynamics from classical to quantum. So that's the plan, and I think I will be able to cover everything. As I said, I'll try to emphasize mostly the concepts. So the paradigmatic slow systems in classical many-body physics, classical soft matter are glasses. So glasses are materials like the picture you see here that, glasses as strictly called glasses are systems which are liquids or fluids that you cool. You cool down and the dynamics becomes slower and slower, and of course that gives the properties and the ability to manipulate the material and to blow them into bottles or to form whatever shapes you like, because the dynamics is low and it's controllable, and eventually if one cools them far enough in temperature, eventually they stop flowing. So glass is an amorphous solid that has stopped flowing. So the dynamics becomes extremely slow, so slow that eventually it completely stops on experimental timescales. And what makes glasses interesting is A, is that they are genetic, and we'll see in a second why they are genetic. But B, because they, this very, very dramatic change in dynamics, going from a system which flows, which is ergodic, which relaxes and thermalizes relatively easily, like a normal liquid, to a material that's essentially solid, on non-observable timescales, happens without a change in structure. So it's a very dramatic change in the dynamics, but the structure, if one looks, is essentially the same. This object I'm showing here, this glass solid object, if one looks microscopically, it looks as disordered and as random in its structure as when it was in the fluid state. So there is no change in structure. So this, if you want, different from one studies in condensed matter textbooks as an undergraduate, where when one changes structure from, let's say, from say something that's that's disordered, like a liquid to a crystal, then of course there is a change in dynamics. But in these systems, there is a big change in dynamics without changing structure. So that's the first big question. And then, this can be quantified, and of course, how we quantify relaxation in physics is by measuring correlations of observables. It doesn't really matter what they are, and this is an example of one of these in a system that forms a glass. And these correlations, like for example, this autocorrelation function, what it measures is forgetting initial conditions. So at initial times, properly normalized, a function like this one is 1, which means that the system, there hasn't been enough time passed since the start of the observation for the configurations that have evolved to have forgotten the initial configuration. As time goes by, this goes down, and under normal conditions, it eventually will go to 0. And 0 in the way that this is scaled means that all memory of initial conditions have been forgotten, except perhaps for some overall conservation, for example, conservation of number of particles if the system is closed, etc. But other than that, the system has forgotten initial conditions completely, and that's what we call ergodicity. It's evolution under the dynamics, such that nothing about the preparation, about the initial state is remembered. What happens in systems which become slow like glasses is that as you change a parameter, for example, temperature, could be density as well, but in this example is temperature as you're making it colder, these correlations become slower and slower. They develop some interesting structure, for example, plateaus, and the times grow. And notice that this is a logarithmic scale. Yeah. And if one is observing the system in such a way, from these correlations, one can extract a characteristic timescale, the typical timescale over which these correlations decay to 0. Loosely speaking, is when the time at which a correlation normalized in this way goes to, for example, 1 over e, or 1/10. Again, the threshold doesn't really matter. What's clear is that as one is changing the parameter that controls the dynamics, in this case temperature, making in this example, the fluid, the liquid colder, this time becomes longer and longer. And what happens experimentally, what I was saying before with a picture of that, that object made of glass, is that eventually these plateaus become so long that at the experimental threshold, there is always an experimental threshold over which one can observe a system relax. Those correlations haven't gone to 0. So now, one question is whether if one waited long enough, these correlations would eventually decay, or are there conditions, for example, a value of a temperature at which these correlations never decay. So this is the question as to whether asymptotically there is a transition towards timescales that diverge, or the timescales are just growing and growing and growing, and one runs out of experimental observation time to see the correlations decay. But in practice, in experiments, there is a threshold which is about 100 seconds. Correlations decay on the order of minutes, for observables which could be rotational correlation functions of individual molecules in the system, in the case of normal liquids, or liquids that form glass. Then one says the system is solid. Yeah. So this is the slowing down, a very elementary statement about how materials of this kind slow down. The second thing, which is extremely important, I said the slowdown does not go hand in hand with any change in structure. The structure looks the same. So in this little example I was showing before, the structure of the system under these conditions, or under that conditions, under those conditions, or even under the conditions where you never see it relax, they basically look the same. They have structure which is almost like the same as the one of the liquid. There is no big change, like when one goes from liquid to crystal. But slowness, what we know in classical many-body system, in dense soft matter systems, is that slowness goes hand in hand with very pronounced fluctuations in the dynamics. And what you're seeing here, and again, I don't want to go too much into the details, is a movie of the relaxation of a two-dimensional liquid in the computer. So this is a computer simulation. It's a liquid, Leonard-Jones liquid, running with molecular dynamics. The details don't matter too much. It's in a regime where it's slow, so it's about to form a glass, but one can still see it relax. But the relaxation is very slow. And what one sees is that there are very, very pronounced fluctuations in the dynamics. And what you're seeing colored here is the particles, not by any structural characteristic, but by a dynamical property. How much have these particles moved? So the particles of the liquid have moved or haven't moved, and this is colored either red or blue and everything in between. And what you can see is that as the system is relaxing, which is becoming, everything will become red. So initially nothing's moved, everything's blue. Eventually everyone will have moved because we are still at ergodic conditions. Everything will be red. The going from blue to red occurs in a highly fluctuating way. And this fluctuation in the dynamics becomes more and more pronounced the slower the system is. So the slower the conditions, the more heterogeneous the dynamics. And this is called dynamic heterogeneity. So then the basics of slow dynamics in classical systems, and the examples are glasses, is that there is no obvious structural change. It doesn't mean that there is no structural change at all. That's an open question, but there is no obvious evident structural change. So the dynamics changes a lot, but the structure doesn't seem to change. And the fluctuations are very manifest in the dynamics. So it really, this is something I say very often, is a situation where dynamics is much more than statics, than the static equilibrium properties. The dynamical properties of systems which are slow are always richer and more interesting. And therefore one has to really focus on trajectories more than configurations. Okay.
One question.
Sure.
Yeah. So the slow timescales that you were showing, or the autocorrelations are averaged over all these sort of fluctuations in fluctuating patterns. Yes. In some sense.
Yeah. Yes. So this, thanks for the question. So this is meant to be the average of over the dynamics at certain conditions, which in the language of trajectories would mean that you start in some initial condition, you run one trajectory and you compute a value of this object. Then you start in another initial condition compatible with equilibrium properties at that temperature. You run another trajectory and you average. And then averaging over all possible trajectories under those conditions, this is the quantity that's shown here.
Right.
So this is an autocorrelation in equilibrium, because you can still be ergodic. Okay.
Thank you. Yeah.
Thanks. So then, I gave you this, this basic message about slowness, and why is it important? Because it's genetic. So what's the ingredients that give rise to slow dynamics and glass formation? Is something that's present in a lot of physical systems. All you need is particles, like in this picture I'm showing of hard spheres, is particles which exclude each other. So they have very simple interactions, very simple and very local interactions, excluded volume interactions, which are very short-ranged. And then you put that, a system of that kind at high density. At low temperatures for liquids, it's like high densities. And what you can see it immediately from the picture. What you become is you become trapped. So because if you want to move a particle, let's say that this particle here wants to move, it needs its neighbor to move first, but the neighbor to move needs the neighbor to move first, and so on and so forth. So the more constrained, restricted you make it, by increasing the density, effectively perhaps by reducing the temperature, the more collective and cooperative the processes, the rearrangements that you need in order to relax. To relax, a particle has to move away from its initial position, but to do so, the neighbor has to move away because it's blocking it, and the neighbor of the neighbor, and so on and so forth. Yeah, it's like it's like taking public transport in the rush hour. We know, we get jammed up by other people all the time, and then that the motion becomes sluggish and slow. So this is essentially the same physics, and this is why, because these are ingredients that are present in many in many systems, typically in soft matter, but also in other systems in condensed matter and so on. glassy-like physics, slow down like glasses, happens a lot. It's very common. It happens in liquids, it happens in colloids, in granular matter, and then you can extrapolate these ideas to lots of problems in biophysics or in harder condensed matter and so on. Okay, so then the question is, how does one think about this problem? And there are two ways to think. Roughly speaking, there are, if you want, two schools of thought. I will take one of those two. One is thermodynamics, and I'm making a cartoon here, which is saying, well, motion effectively happens in some random landscape, like a random free energy landscape. And these are ideas that have their origin in systems with disorder, like spin glasses. Spin glasses are magnetic, magnetic alloys, magnetic systems of spins, which interact with fixed but random interactions. Yeah, and then that gives rise to some random landscape. And of course, a couple of weeks ago, Giorgio Parisi got the Nobel Prize for his theory, his mean field theory of spin glasses. So that gave rise to a lot of thinking that has been applied to other systems like structural glasses. But structural glasses are not disordered. They're just particles with a very simple interaction, excluded volume, like in this example of hard spheres. So what I'm going to argue, and the point of view I'm going to take, and it's not so much to discuss about what's the explanation of the glass transition, it's just to build there in a modelistic way, is that what I've been telling you is that this slowness is basically a dynamics problem. It's a dynamical problem. It doesn't, the dynamics does not come from some change in statics as it would be in this perspective. What really matters is the connectivity of configuration space. Again, if you go to the picture of hard spheres, they are not special configuration. They are not. The problem is not one of finding special arrangements. Basically all arrangements are equivalent of hard spheres. The problem is going from one arrangement, one configuration to another is problematic. So it's really how configuration space is connected. Maybe two configurations are not terribly different, but connecting them dynamically requires a very convoluted path. And this is what happens at high densities. And this is the origin of slowness in this perspective. And this perspective can be furnished, and one can study it in some detail through models which have kinetic constraints. And this is the class of models I'll discuss. And these are ideas that go back a long way. Originally, the two main names that initiated this way of thinking are Phil Anderson in the late 70s, like many other important ideas in condensed matter, and Hans Andersen from Stanford in the early 80s. And building on that, it's built the corpus of work that I'm going to focus on. Okay. So what are constrained models? What are kinetically constrained models? It is, like in StatMech, we always try to take the problem, try to distill the main questions, and reduce it to models which are very simple, and we can ideally solve or study in detail, and then take that insight back to the original physical problem. That's what I'm going to do now. So this class of models realizes this thinking that what matters really is the dynamics, and the dynamics due to the connectivity of configuration space. So let's consider probably the simplest problem in statistical physics, in the dynamics of a statistical physics problem. Let's imagine we have a chain of binary variables, Ising spins, and we have dynamics which is totally uncorrelated. So our dynamical rule is written here. I'm going to call this unconstrained. So we take a spin and we flip it, and we take another spin and we flip it with a certain rate. So now that's a stochastic process. So there is a probability. It's a trajectory is a configuration evolving, and if one averages over trajectories, has a probability of being in a certain configuration, and that probability evolves according to a master equation. And that master equation, the dynamics, is generated by an operator. And I'm using the language of continuous time Markov chains, but it's not really too important. It's because it's easier to write. So now this is the simplest Markov Markov's, Monte Carlo simulation, you can imagine what we teach at undergrad. Is say, just take a bunch of spins and flip them and see what happens. Yeah. So you choose a spin, you flip it, choose randomly another spin, and you flip it. And then you get trajectories of this kind. And of course, it's not surprising that the trajectories look completely disordered without any interesting features at all. And furthermore, the stationary state, if you run this dynamics, which is a vector that annihilates this operator, so it's the fixed point of this stochastic dynamics, is also completely structureless. It's the sum over all configurations, because a dynamics of this kind, becomes thermalizes, goes to an equilibrium state, which is the sum of all configurations. Yep. So then,
excuse me. So this gamma depends on the temperature, is it?
So this rate for the moment is just a number. Let's forget about temperature for a second. Yeah. Okay. We say with rate 1, yeah. We can put a number here and we run this dynamics, which in practice is you choose a spin at random, you flip it, you choose another spin at random, you flip it. Yeah. Mm-hmm. One could have a variant of this where it's more favorable to flip down. Sorry, it's more favorable to flip down than to flip up. You could say, oh, going down, I have a rate, let's call it 1 minus C, and going up, I have a rate C, and C is less than a half. Yeah. Right. And it's like saying, it's like a bunch of spins in a magnetic field. Yeah. Right. You would still get something like this. Then your equilibrium wouldn't be so trivial, but still would be completely non-interacting. And the trajectories will look completely non-interacting as well. Okay.
Thank you.
So now I'm going to make a constraint model. And one particular one, the so-called East model by Joseph Jackley in the 90s. And this is a really important model for glasses, and that's why I'm focusing on it. But it's very, very simple. So now what we do, as we just discussed, this was a constant rate, which is just saying all spins are flipped at a certain rate. Yeah. Or each spin survives without being flipped for some time that's given by this rate. Well, what if we make, nothing prevents us from making this rate operator valued. Yep. And in this particular model, this operator valued rate has that form. And what it means is the following: is a spin to flip, a spin can flip only if the neighbor is in the up state. Yep. And in this simple example, the flip doesn't really, it has the same probability to flip up or flip down as long as the neighbor is in the up state. If the neighbor is not in the up state, then the transition of the spin is not allowed. So 1 cannot go to 0 or 0 cannot go to 1. Okay? And this is what we're calling a constraint, an operator valued rate. Now, this is not an energetic interaction. It's a purely dynamical interaction. It's saying whether the transition can take place or not. The stationary state is the same as in the previous one. It's exactly the same stationary state because this vector still annihilates this operator. Yeah. But the dynamics are completely different. So what we have is now we've split thermodynamics and dynamics. The thermodynamics of this problem is trivial. The dynamics is not. What you see is that you have fluctuations. There are regions of space and time where nothing's happening. And nothing's happening because the constraint is not satisfied, so there can be no flips. And there are other fluctuations, which are regions of space-time, that a lot of things are happening. Yep.
Sure. One question, these constraints always have to come in the form of certain processes being completely forbidden, or can I just make the rates very small and is there a continuous limit of reaching this, or is it something?
It's a good point, because one could say, let's make the constraint n I minus 1 plus some epsilon. Mm-hmm. Yeah. So in the jargon, this is called a hard constraint, yes or no, and the previous one is a soft constraint. Mm-hmm. And what you see, what it does is the soft constraint behaves like a hard constraint or not, depending on the conditions of the problem and how large that epsilon that allowed the flip to happen, how large it is. Okay. Mm-hmm. So And it's a really good problem. And there's a big literature on constraint problems, hard constraints, soft constraints, what that means.
Right.
And,
right. Yeah. Okay.
And by the way, the other thing is when one thinks more physically, I won't go into this. If one goes back to problems like glasses and so on, how a constrained model could emerge, is much more likely that it emerges as the limit of a soft constraint, that in certain conditions the constraint is dominant, than as a hard constraint that's written here. But they are easier to solve as a hard constraint problem.
No, my only question was because this W matrix, I mean, depending on what the hard constraint is, at some level might have lower rank or may not be invertible in some ways, whereas in a soft it will.
Well, and that's something, if I have time, I'll show now in the 2 or 3 slides. A very important question when one analyzes this is the reducibility properties of these dynamics. Is this dynamics irreducible in the sense all configurations are connected, or is the constraint so strong that some configurations are disconnected?
Okay.
This is very important. I might say something in a minute.
Sure.
Yeah,
sure.
thanks. Okay. So again, I don't want to spend too much time here, but just say that, this is an example of a constraint dynamics. This one, we'll see in a second. And the key thing is the separation between stationarity and static properties and dynamics. Dynamics, already this trajectory, this dynamics is clearly very rich and fluctuating. And indeed, what you're seeing is a coexistence of 2 dynamical phases. And this can be, really quantified. And because here you have a dynamical phase, which is empty, which is inactive, nothing's happening. And then here you have regions of what's an active dynamical phase. And you start to see the dynamics of the liquid and the glass contained in this extremely simple model. And this way, this is so powerful. And then just coming to the question, one can I wanted to just give us an example. There is a whole class of problems. One can put a much stronger constraint. Yeah, this is become popular because it relates to problems with Rydberg atoms. It's called the PXP model. The details don't matter. And what happens is that this problem is exactly the question you asked. Let me just put it here. What happens is that the East model I was just discussing, this state space has one configuration which is isolated. If everyone is 0, you can never satisfy the constraint and no one can ever flip. But all the other configurations are connected. And in a large system, this is not relevant. So what one really has is slow fluctuating dynamics inside there. Well, if one puts a stronger constraint, the constraint is so strong that all that happens is that you break state space into exponentially many disconnected pieces. And if one looks at the dynamics in one connected piece, there's nothing really interesting. So this is just to say, this is a way to define dynamic stochastic models. And depending on the constraint, you get very different behavior. So I'm going to focus on this one on what follows. It's like in a sweet spot of making dynamics interesting without breaking it too much, keeping it ergodic, or keeping it reducible and actually ergodic. Irreducible and ergodic. Okay? So, yeah, this is another example. If one starts from the most unfavorable configuration, one says that, under these dynamics, it takes a very long time to become ergodic. Yeah, the coexistence, is one phase and another phase. This thinking that one can apply to trajectories coming from the ideas and methods of phase transitions that we know from equilibrium as well, but in the dynamical context. And just to say, well, this looks like a very simple model, but if one now endows this with a temperature, in the sense that flipping up is not the same as flipping down, these rates I was calling 1 minus C and C, and this could be dependent on temperature. So flipping up could have a rate C, which is e to the minus beta, some energy scale for flipping one spin, like if the spins had an energy and this was thermal. One can work out, I won't go into the detail, that the relaxation time for this model has this super exponential form. And if one takes all the data available for liquid, well, to date of this paper down here, one sees that this super exponential form fits the data very well. So all I'm saying is that we started from the main idea of how to think about slow dynamics in terms of connectivity of space. With that idea, you can define simple models. Those simple models can be studied. They give you insight, conceptual insight into the physics, and particular models like this model actually give you scaling properties that seem to be pretty good for the phenomenology. So it's not just an interesting question in StatMech, but it also, seems to have applicability for the original problem. Okay. Any questions up to now? If not, I'll move to the quantum side. So all I wanted to say was to emphasize what's the main aspects of slow dynamics in classical systems, around the problem of glasses and the glass transition, how to think about it in terms of constraints, and showing you that it's a simple set of ideas that allows one to solve some of these models, and from solving them or studying them in detail, one can both explain the phenomenology of the original glass problem, but also construct a way of thinking about slow dynamics in general. Okay.
Mm-hmm. Yeah.
Now I want to
yeah. So this reminds me of the cellular automata dynamics, in which you have like a triplet goes to so a single thing at the center, and depending on your rules, maybe 0, 0, 0 of course is something trivial, it always goes to 0, and 1, 1, 1 also goes to 1, and it's some rules in the middle only, which gives rise to interesting configurations.
Totally. This is, you're 100% right. And if you give me a little time towards the end, I will talk about cellular automata. Okay. So cellular automata of the kind you're referring to are also constrained, and the nature of the constraint is very similar to the one I described here, except that the dynamics progresses, for example, synchronously, etc., and in some cases deterministically. But the constraints are there, and a lot of the physics that I've been describing, or some of the physics I've been describing, appears there. Towards the end, I will mention them. So thanks a lot for that question.
Thank you.
So let's do quantum, and I tried. I've spoken for half an hour. I'll do 10-15 minutes, and then I'll wrap up. So now some basics of quantum relaxation. First, this has been a subject of study, very intense study for the last 10-15 years. Yeah, and a lot of things are understood, and there are lots of questions as well. Two things that are understood pretty well are the following. The first one, if you take a generic quantum system, many-body quantum system, not a special one, but a generic one with generic interactions, they quote-unquote equilibrate, which really means that even if one runs unitary dynamics, when you measure observables, they go to stationary values. Yeah, and this is an example from one of our papers, but there are millions of these examples. This is some Hamiltonian, comes from the Rydbergs. Never mind, it's a spin chain with some fun interactions, particular interactions, and then you measure some expectation values, and what you see is that you run the dynamics on the computer, and those expectation values become flat. Yeah, so this is called equilibration in this field. Now, becoming stationary doesn't mean that you're ergodic, because the value at which you go might depend on your initial condition. Ergodic is also forgetting initial conditions. And what's accepted and relatively well understood as well is that most quantum many-body systems also thermalize. And by thermalization, it's a statement about ergodicity. It's not only that they go to stationary values, but these stationary values are equivalent for local observables to the values you would get in a thermal state. And basically, the idea is that you have a big system that's evolving unitarily, or you're looking at at operators which are reduced to some subsystem, and for that subsystem, the rest behaves as the thermal bath. So a big system can behave as its own thermal bath. Yeah, and you know, there's been a lot of work of trying to understand this, and you know, the paradigm or if you want, and the actual behavior is similar to that of random matrix systems with the same symmetries. Yeah, and this is the basic ideas about quantum ergodicity. However, there are exceptions. One exception, of course, are integrable systems, where there are many conservation laws. But integrable systems go to something akin to equilibration, to thermalisation, that's called, you know, it's a generalized ensemble where you not only conserve, you know, have a parameter like the inverse temperature associated with conservation of energy, but you have many of these parameters associated with all the conservation laws. And then the systems that generically don't seem to become ergodic are called many-body localized systems. If you have a quantum system with disorder, and the disorder is strong enough, you can avoid thermalisation. And another way of saying it is, and this was the original understanding by Pascual Leiner and Schuller, that Anderson localization, which is a single body problem, can survive interactions and become a really localization in a many body sense. And it was, you know, David Hughes who really, you know, made this, helped make this a big field. So this is non-ergodicity in the presence of disorder, quenched disorder. So now, if I put my classical hat on, I can make this little table. On the left, we have quantum systems evolving unitarily. And on the right, we have classical systems evolving stochastically. Yeah. And thermalization is like what we would call equilibration, going to the thermal state, like the liquid, if you want. Yeah. Then MBL is being non-ergodic in the presence of strong disorder. And as I said, this could be like spin glasses, systems with disordered, externally imposed disordered interactions. And we know that spin glasses have phase transitions and they become non-ergodic if the disorder is strong enough. But then there is a gap in the middle. I've been telling you in the first half of the talk about structural glasses. They have no disorder. They're essentially metastable. You know, they don't necessarily become non-ergodic asymptotically, but perhaps only on very long times. And the reasons why they are slow, is due to the presence of dynamical constraints. Yeah, not disorder. So is there something similar on the quantum side? And this, you know, I'll wrap up in the last 10 minutes trying to argue that the answer is yes. Yeah. So then kind of the procedure is almost obvious. So up to now, we've been discussing, in the first half, I was discussing classical models that evolved stochastically. So there's a master equation for a Markov process, and the Markov generator had constraints like the East model I described. Yeah. They were the open dissipative. Yeah, they interacted with an environment that's the source of the fluctuations, and they evolved stochastically, and they were classical. So now what I can do is that these are operators. I can write similar operators and call them a Hamiltonian, and then run quantum coherent dynamics. So use those operators to evolve a quantum state unitarily. And the question is, do the constraints that restricted the connectivity of configuration space in the classical problem and gave us low dynamics, large fluctuations, and so on, do the similar constraints do something similar or perhaps different or perhaps interesting in the quantum case? Yeah. So then let's define the quantum East model. So if you remember, so the East model had, you know, a term that flipped. So the generator had the part that flipped. So it's a continuous time Markov Dynamics in the generator a few slides back. Well, I won't go all the way back. And it had a term that flipped and a term, as usual, that, you know, helps you conserve probability. And the key thing was that the rate was an operator. So you could only flip if the neighbor was up. Yeah. And now we're going to put a parameter to have a parameter that can control whether the system is slow or fast. Yeah, and this parameter just tilts the balance between kinetic energy and potential energy. Yeah, and this for historical reasons is e to the minus s, could be called lambda, could be called anything. Yeah. Now this operator, when that s is 0, is at a stochastic point. It's also sometimes called a Rox-Archivalson point, you know, for quantum many-body systems. So now the first thing we can do is to look at the ground state properties of this. And the ground state, because this is also related to a Markov generator, the ground state is also related to the large deviations, you know, properties of certain objects in the stochastic problem. Never mind, you know, it's the spin flips in the trajectory. Never mind. There is a connection between the spectral properties, the low-lying spectrum of the Hamiltonian, and some stochastic properties of the original stochastic problem. But never mind. The key thing is that this operator, you already start to see how this as a Hamiltonian, as a unitary problem can be interesting. This Hamiltonian has a quantum phase transition, which is of first order, happening at s equal to 0 in the large size limit. This can be done by finding, you know, the ground state using matrix product states, because these are spin chains. It's, you know, it's a good technique. Basically what you see is you have, you know, the ground state has two branches that cross, and this crossing, this is the derivative of this negative of the ground state energy as a function of this parameter there. And as you're making the system larger, you see that the derivative becomes sharper and sharper. That's a first order transition. Yeah. So the ground state has a phase transition. Yeah. So now I'm going to skip a couple of things and say, well, how is the dynamics? We already see that the ground state has something interesting going on. There seem to be two regimes depending on the value of S. Yeah. And we'll see in a second that the ground state is localized or extended depending whether S is positive or negative. Okay. If one runs dynamics, now it puts this in the computer and runs unitary dynamics. Of course, you cannot do it for large sizes. You can do it only for small sizes. What you see is that for one value of S, relaxation, quantum unitary relaxation is fast. If you prepare an initial condition where all spins on one side are up and all spins are down, because of the constraint, the spins over here cannot flip because they can only flip if a neighbor is up. So this front has to propagate. When S is negative, it propagates quickly and the system becomes quickly ergodic. If you measure observables, you know, the observables thermalize in the sense that an observable for the same initial energy, even starting from different initial states, transiently might go in different ways, but eventually they all come together. So this, for S negative, it's doing what one expects, thermalizes. For S positive, the converse is true. The propagation of this front that divides spins up from spin downs is extremely slow, happens to be logarithmic in time. On computer timescales, you never see these observables. They do become flat, stationary, but they don't come together, despite the fact that in this example, they're all starting from the same initial energy. So dynamics is remembering initial conditions, at least for the timescales you can do simulations on. Okay? So the constraint in this quantum problem is doing something big at some, you know, at positive values of this parameter S. So it's basically, you know, and everything else builds on this. And I'm going to finish so one can, how long do you want me? I think I have about 5 minutes.
I think we can go on for 5 more minutes.
Yeah, so I'll say a couple of things and I want to come to this, you know, to try to address some of the questions. So one can then, because of the simplicity of this model, one can go further. As I say, oh, is it that this is a spin a half problem? Well, one can define a bosonic version of this model in a limit of large, large occupation on each side. You can go to some semi-classics, you can do large sizes, and again you see the same thing, fast propagation or thermalization. So it's really the constraint that's doing the job. The ground state is localized on one side. Yeah, sorry.
So just to understand, how does S changing from negative to positive add the constraint? I mean, what is it doing in terms of the actual Hamiltonian?
It's the system is always constrained.
I see. It's just
and what S does is simply make the kinetic energy, the bare constant in front of the kinetic energy, larger or not than the potential energy. And what happens is that as one changes S, you know, the ground state becomes localized. You know, so this is the inverse of the localization length. On one side, the ground state is extended, and on the other side, the ground state is localized. And this has, you know, I don't have time to describe, but this drives everything, because on the localized side, the ground state looks like a 1, you know, with open boundaries. You have a 1, you have an exponential tail and a bunch of zeros. Yeah. And then I'm going to skip, but with this construct, you can go from the ground state, construct states in the spectrum, which are all very slow. And I'll skip what you're doing. But essentially, you can construct states which look like the gluing up together of ground states. Yeah. And this gluing up together of ground state gives you excited states, but they have localization properties and slow dynamic properties due to this localization. And this you can do it systematically and not completely rigorously, but, you know, essentially exactly. Yeah. Okay. So, and the nice thing is that usually the, you know, many body localization and this localization, first of all, this slow dynamics and this emergence of non-thermal states happens due to constraints, nothing to do with disorder. There is no disorder in this problem. The second thing is that it's very easy, not easy computationally, but it's easy, you know, to formulate, to extend this to 2 dimensions, because one can define, you know, an East model in 2 dimensions where, you know, a spin can flip if the neighbor down or the neighbor, so the neighbor to the, I was doing, and so a spin can flip if the neighbor there is up or if the neighbor there is up. That's a 2-dimensional version of the East model. The ground state is localized, computational is more complicated still, but the principle is the same. You can construct excited states from this localization of the ground state in 2 dimensions. Okay. And then the final thing I want to say is that there are many other interesting constraint models, which are both interesting classically and they are interesting quantum mechanically. One is, I will skip, but one are Fredkin spin chains where, you know, particles can flip, hop from one side to another, like in what's called a simple exclusion process with some extra constraint on the neighbors to the left and to the right. And this relates to, you know, to random walk excursions and what are called Fredkin paths. And, you know, many of the things we saw for the East model can also be done here. Then there are models where the constraints are not explicit, but they are implicit. You know, and then the one that's my favorite is the triangular Plaquette model, sometimes also called the Newman-Moore model, where you just have energies and you have spins, and they have some interaction between triplets in certain geometries. But these models have are dual to models of defects, and these defects propagate with constraints. So they have not explicit, but effective kinetically constrained dynamics. And it so happens they're very connected to what's become a bigger field now in the last 3 or 4 years about fracton, about about excitations in certain quantum systems which are exotic. And the final thing that relates to not quite there. Other classes of models are tiling-s, dimer coverings and tiling-s. If you have if you have to tile space with tiles of a certain kind, again, constraints emerge, and the dynamics is rich and glassy and interesting, both classical and quantum. You have constrained lattice gases. For example, if you have a particle that would like to hop to that empty space, but cannot do so because it has a certain size, and there are neighbors which are not occupying the site it wants to go to, but restrict the space they want to go through. And again, you can play the game with this. You see that relaxation is heterogeneous in terms of entanglement, and that's basically the same. It's a quantum manifestation of dynamic heterogeneity. And then finally, to connect to the question that 5 minutes ago, there are kinetically constrained circuits. And these are cellular automata. In particular, the ones that we've looked at are deterministic. where you have a cellular automata defined in terms of binary variables, and there are gates that you apply, and the flip of the central spin depends on the state of the neighbors to the left and to the right. And these constraints are similar to the others. And some of these systems are integrable, and you can solve them exactly. But nevertheless, you can see that the trajectories have fluctuations, interesting fluctuations, because of the constraint. Okay, and this is a very interesting class of problems that you can study both classically, and people are looking at them more recently quantum mechanically, where again the constraints dominate the physics. Well, this is basically all I told you, and these are the people whose work I described, and I'll stop there. Thanks.
Thanks, Professor Garrahan. Let me first see if there are questions from anyone else. So I had one question, which was actually a couple of questions, maybe again. So at least in equilibrium theories, often in quantum theories, at least as I know, constraint Hilbert spaces and etc. give rise to what people call gauge theories. You basically impose the constraint using some Lagrange multiplier, fluctuations of that become some sort of a gauge field. And so, are there similar techniques developed for the dynamical or kinetic constraints, which are not necessarily?
They haven't been used that much. So two things happen. Let me see if I have an example. If I think, let's take this one and that one, or this one versus the others. In a problem like a covering, the constraint restricts your configuration space. Your configuration space, you cannot have a basis of configuration space, which is a product basis. Right. And the dynamics in a constrained space will be constrained. And this is what happens here. Now, a problem like this one, all configurations are available. So your state space is not constrained. It's only how you connect it. And in particular, this one is effective. So that's the slight distinction, is that constrained systems, the ones which don't break space, are ones where you don't have the problem of not having product basis, certainly in the large size limit. And then the complication comes through the dynamics. In systems which break state space, you can have two things. You can have the ones where the dynamics inside a component is not too interesting, like in the PXP, or dimers, coverings, etc. On top of everything, have a very interesting dynamics. But of course, they have the extra complication that you have to be careful about how you formulate the problem to live in the space that respects the constraints on configurations.
I guess the second question I had was, is there any? And I mean, we saw some examples of even constrained models where, depending on parameters, you can be, the dynamics can be fast or slow. So, is there some understanding of what kind or how to classify constraints which lead to actually slow dynamics?
Yes, and to varying degrees. There is a lot of study in the physics literature on understanding models and trying to get some insight into why they behave as they do. And the basic idea is that the stronger the constraint, the slower you are. The lower the dimension, the more prominent the constraint. But if the constraint is too strong, you break it. So now, having said that, there is a more recent and much more detailed and essentially exact work by mathematicians like Cristina Toninelli and co-workers, and also the group I mentioned on the East model, Schlebon, Fagionato, Martinelli. So there are people who are interested in stochastic processes from the mathematics point of view, and Toninelli et al. Have a classification of these constraint models, in the sense they classify them as to whether they have a dynamics which is ergodic, or they have a dynamics which is non-ergodic, or they have a phase transition between them, and the characteristic of the phase transition, both in systems which conserve density and which systems which don't. First, the ones which don't conserve, which are easier, and then the ones which do conserve, which are less easy. So there is that classification, yeah. And it's very interesting. And some of those, by the way, some of the mathematical results can be very insightful as well. For example, Martinelli, Fagionatos, Le Bon, when proving, when obtaining the correct coefficients in this scaling time scale, the scaling super Arrhenius time scale, they uncover properties about the entropy of paths, which it's complicated mathematics, but it turns out to be important physics as well. Yeah.
Thank you. Any other questions?
Yeah, I have.
Yeah, go ahead.
So, yeah, so you introduced this triangular Plaquette. I mean, you showed this triangular Plaquette model where this energy is written as sum over some product of three spins.
Yes.
On, where the spins are on three vertices of triangle. Now,
yes.
For that particular model, what is the minimum energy configuration?
Oh, so yeah, good question. So what you have is the triangles are upward pointing triangles only. Yeah. So so depends on boundaries, but in principle, you can make these positive in 4 different ways. The 4 spins, the 3 spins all up, or 2 spins down and 1 spin up. There are 4. So in principle, this could be like a spin liquid, yeah, in the sense that there are multiple ground states depending on what you choose. It so happens, and it's connected to cellular automata, the calculation of the ground states, by the way. It so happens that if you put them in periodic boundaries, we have a period 2, there is a unique ground state, which is everyone pointing up. And if not, you have a number of ground states that depends on if you have open boundaries, if you fix two sides of your, of your parallelogram, then you can have multiple ground states, but it depends only on the linear size and not on the volume. So in the large size limit, there is no entropy from ground states. But in any case, yeah, that, locally, there are many solutions to this. Globally, there might be 1 or a few, depending on boundaries.
Okay. So, because I was surprised because as you said that there is ferromagnetic type of interaction. Also, I mean, where the all spins are up. So,
yes.
I mean, is it necessary in that case that can I approximate the Hamiltonian as the ferromagnetic interaction and go with that in that case? I mean, is it necessary to have this 3-spin interaction?
Well, it's a model, so it's necessary. Okay. What the distinction between, say, this and the 2D icing with ferromagnetic interactions is that because of this construction, the defects are point-like. Yeah, they are these, localized plaquettes, so you don't generate domain walls. And because you have point-like defects instead of domain walls, you don't have a phase transition. The system is always disordered in a disordered phase at any temperature. But then the dynamics is interesting because these point-like defects evolve in a constrained way, effectively, under spin flips.
Right. Yeah, thank you.
Other questions?
Sorry, I was
yeah. Okay, go ahead, Gautam.
Yeah. So these kinematic constraints, do they lead to? Maybe it's a vague question. Do they lead to broken ergodicity in the configuration space, where? Okay, I'm trying to make a distinction between constraints which are of equality types and constraints which are of inequality types. Like divergence of E equal to 0 in a gauge theory, it's an equality type constraint. And therefore it cuts down on the dimension. And your kind of constraint, does it cut down on dimension, or is it like, does it pick out does it pick out subregions of the same dimension?
So
Dynamics.
I'll try to give an answer to the extent I understand what you're referring to. I think again, this comes back, in part comes back to a question of this kind. So tilings, the tilings have a constraint which you can formulate as and this is what's referred to as a gauge theory, and they restrict the state of space, the space of configurations, and then you can try to resolve it. The ones I was describing before, like these ones, etc., and in the classical one, the east, etc., and so on, are constraints which only affect the trajectories, the paths. So if I do the space of all trajectories, configurations evolved in time, the constraint removes a lot of those configurations. So if you want the space that gets cut by the constraint and reduce dimensionality in that sense, is the space of trajectories. Because now, so I have my configurations, and without the constraint, I can evolve the configurations in any way I want. With a constraint, I have to evolve them in a particular way, because many transitions are not allowed. So that's the space that would get, the space of trajectories would get, cut through by the constraint. Whether one can formulate it as dimension, reducing the dimensionality in the sense of, in the sense of gauge invariance, which really is a statement about redundancy of degrees of freedom, I don't know. So
the initial data is arbitrary, isn't it? I mean, in the other case, the initial data is arbitrary, and then the dynamics has some restrictions. So
yes.
So that does not sound like gauge theory, because in gauge theory, the initial data itself gets restricted. What kind of electric field and magnetic field you can specify on at the t equal to 0 surface itself is not arbitrary. I mean, it has to satisfy divergence of E equal to 0. On the other hand, your initial data is arbitrary, but the dynamics has some constraints.
Yeah, exactly.
Okay, it's just to understand. Yeah, okay, thank you.
A related question. So in these fractonic systems, the statement somehow is that there are particle-like excitations that can only move in certain directions or in lower dimensions and so forth.
Yes.
So the example you have, should I think of it as something similar, but even without any point-like excitations? I mean, there the trajectories are written in terms of some object that's moving. But in your case, you are saying something more general about restricting trajectories without necessarily having a localized object moving in lower dimension. I mean, I'm trying to understand the connection between your...
No. It's a good point. It's a good point. Let's just try to, let me try to use this as an example. This is a classical fracton model. Yeah. So in this model, the fracton, so this model, the fracton is an excited plaquette. And the reason is that I can construct a spin texture such that there is a single plaquette which is excited, where the value of this is not 1. And that's a localized object, and that's what you would call the fracton. Yeah. And it would be a fracton because the elementary units of, the elementary degree of freedom is the spin. A spin belongs to 3 plaquettes. So if you flip a spin, you produce 3 of these excited plaquettes. But you can construct a spin texture where one of these objects is isolated. Yeah. So that's the localized object that propagates in a complicated way. So this fracton propagates in a fractal, this is 2-dimensional, but there is an underlying, Sierpinski cascade, like a Pascal triangle structure. And the fracton, essentially propagates there. Or there is an underlying fractal dimensionality to these excitations. Okay.
Yeah.
then why are these fractons stable and slow and behave like fractons, as now they are called? Because if I have an isolated fracton, here I have the isolated fracton, and I want to move it about. Yeah. So now this fracton, if I flip a spin, creates 2. Yeah. And then you know, if I have 2 and I flip another spin, I create another 2, and so on and so forth. So to propagate this one, I need to create others. And if I have no fracton at all, and I'm at low temperatures, I cannot have dynamics because it's too costly to flip a spin in the absence. So effectively, the fractons propagate in a constrained manner. I need 1 fracton to create 2, and then that 2 can kill this one, but they propagate and so on. But for this model, that's, if you want, is the low temperature behavior. If I turn temperature high and I have enough energy, I can just create flip all the spins, and I have fractons everywhere.
Right.
So now, if one reduces the dynamics to the one of, you know, these dynamics I'm describing here, and saying, oh, now I impose the strict constraint, I can only flip them,
Yeah,
in the presence of another one.
yeah,
Which at the beginning was, oh, if the constraint which is soft here is made hard by hand,
yeah,
then I have a theory of that kind. I can propagate my fractons only in a particular complicated way.
right, right.
So there are other constraint models. If I do the same model on a square lattice with 4 spins, then I have objects that propagate in lines and in columns, and you know, it's like type 1 kind of fractons.
Right.
Of course, more complicated fractons have other conservation laws, not just the conservation of the fractons. Sometimes not the conservation of fractons, but conservations of, if the fractons can have positive and negative charges, and then there is a conservation of charge, so you can create and destroy fractons, but there's sometimes also conservation of dipole moment.
Right.
And then you can write a, you know, that's what I'm saying is that this is a good starting point as the effective theory, then becoming a hard theory.
Right.
Yeah.
Right. Thank you.
Thanks.
Okay, so any other questions? If not, let's thank Professor Garrahan for a very, very nice and illuminating talk, and we really enjoyed.
Thank you very much.
Thank you.
Thanks.